Okay, thank you. Thank you. Introduction to Maclaurin and Taylor polynomials. What we're going to do in Chapter 8, chiefly, is approximate weird functions with polynomial functions. Here's why, and don't write any of this down, this is just intro, but I can have a weird function, like x times the log natural of x, sine x or something like this, which is horribly weird. And then I can have polynomial functions, like 2x squared plus 5x plus 3. And if I could approximate this horribly weird function with a polynomial function, that would be a good thing. Because adding, subtracting, multiplying, and dividing polynomials with each other is very, very easy. Getting derivatives of polynomials is very, very easy. Doing those things with weird functions is really, really hard. We hate weird functions. We like polynomials. And so my goal is to take weird functions and approximate them with polynomials. Now, when you graph a weird function, and of course this isn't the graph of that, just pretend, but let's say I've got a weird function whose graph ends up looking like this, okay? Well, I'm not going to get a second order polynomial. I may not even get a 10th order polynomial that looks like this over the entire domain, but most functions, I only care about them over a small domain. Like if I had a function that modeled heights of children, okay? Well, that function only has to be good from, a foot to 4 feet or something. I don't need a model that'll model heights of children from 0 to infinity, because kids aren't infinity tall. You know what I mean? Or if I had a function that modeled GPA of kids, like, if you tell me your income of your family, I'll tell you what your GPA is, that sort of thing. Well, that only has to be good for GPAs ranging from 0 to like 4, right? If it's unweighted. I don't need a model that models GPA versus family income from 0 to infinity when GPAs are only, have meaning from 0 to 4. And it's the same sort of thing with weird functions. If this weird function is modeling something like the profits of your company or the amount of water in your reservoir, usually it's only has meaning for us over a small domain. And so our goal is to get a polynomial function that will model this over that small domain. So I'm not going to get a polynomial function that models this weird function from negative infinity to positive infinity, but I could get a polynomial function that models this over some small domain. You see? So let's say this is my polynomial function, right? And I'd say, well, this polynomial function is a terrible approximation of the entire function, but it's a real good approximation from there to there, right? It totally approximates my function from there to there. You see? And so our goal is not to have polynomial functions that's going to overlay my weird function from negative infinity to positive infinity. It's just to have a polynomial function that will overlay my weird function over some domain, over some small interval, where I say, hey, if this happened to be a function modeling the amount of water in a reservoir, then this second degree approximation is the formula I would use. I'm not going to use that formula. I'm going to use that formula, because that formula is good over the domain that I care about. Okay, I hope you're getting that. This is all intro, And so how do I determine this domain, this neighborhood, if you will? How do I determine this neighborhood over which I want my approximating polynomial to be a close, approximation of the weird function? Well, the way you determine it is actually by choosing the center of the neighborhood. You choose the center of the neighborhood that you care about, and you say, I'm so sorry, Kim. I'm watching you chew your gum and make bubbles, and you keep doing it. It's just very cute. That's funny. Every time I turn around, and Kimberly's like got a bubble like this, and I turn around and Kimberly's going nom nom nom. I don't know. It's cute, but it's okay. It doesn't bother me at all. It's very cute. So the point is, you're going to choose this one point and say, hey, that's the center of my neighborhood. Hey, Iqua, you ready to do the exam? Okay. I mean, you're 10 minutes late. Are you prepared? Like, did you study and stuff? Oh,
No.
okay. Then if you need help after class, you know, I'll give you as much time as you need.
Thank you.
Yeah. I mean, the test is hard enough. Oh, there's someone got your homework there, too. Okay, great. Let me tell you the second intro thing, the second conceptual thing I'm going to tell you. You know how we construct this approximating polynomial? And we do construct it. Here's what we do. Once we've determined what the center of my neighborhood of interest is, I just do this. I say I'm going to choose a polynomial function. Let's say it's a second degree approximating polynomial. I'm going to choose a second degree approximating polynomial function such that if this center point is called C, C for center, I guess, if that center point of my neighborhood that I want to do my approximation is C, then I just make sure that f of C equals P2 of C. I make sure that f prime of C equals P2 prime of C, and I make sure that f double prime of C equals P2 double prime of C. That is the way I construct my approximating polynomial, and the way I get my polynomial to hug the weird function for a particular neighborhood is really to just choose the center of the neighborhood and then make sure that the functional value, the slope of the tangent, and the concavity of my approximating polynomial are identical to that of my weird function. And if I do that, then I end up getting a second degree approximating polynomial that hugs my weird function, at least for a certain neighborhood. Eventually it departs, you know. Let's say I wanted a third degree approximating polynomial. You know, let's say my approximating polynomial looked like this, okay? Then all that means is I have to also now make sure that the third derivative of my weird function evaluated at C equals the third derivative, and that would be P3, the third derivative of my approximating polynomial evaluated at C, and so on. If I wanted a fourth degree approximation, then I'd have to make sure that the functional value first, second, third, and fourth derivatives at C are identical to the functional value first, second, third, and fourth derivatives of my weird function. And that's how I pull this off. Any questions on this before I go on and start the actual work of creating these approximating polynomials? Okay, well then, hey, let's get started. Let's do the thing. And now go ahead and start writing stuff. Here we go. Example number 1. Get a polynomial approximation of f of x equals e to the x power. For my weird function, I gotta choose something kind of easy because this is the first time doing it. So I'm gonna choose something really, really easy. Get a polynomial approximation of f of x equals e to the x power. And then I need to say where it's centered at. I need to say where my C is, where the center of my neighborhood is, where I want it to hug the function. And I'm gonna say centered at x equals 0. Pardon me. Get my notes. Okay. Let's start with a 0th degree approximation. That is, my polynomial function, 0th degree approximation, is just going to be a constant. That's a 0th degree polynomial. That's just a constant. Okay? So all I need to do is find what that value is. Well, here's what I'm going to do. I'm going to get what f of 0 is. That's e to the 0, which is 1. And then I'm going to get what p naught of 0 is, which is just a naught. There's no x in there, so it doesn't matter what I plug in, I get a naught. And then I put them equal to each other. So there it is. I have found my 0th degree approximation of e to the x. My 0th degree approximation of e to the x is p naught of x equals 1. Let's graph them and see how good this approximation is. Here's e to the x power. And here's my 0th degree approximation. I'd like you to notice that at x equals 0, my 0th degree approximation is right on. It's perfect at x equals 0. But it's not very good as you get any distance from 0. You see, e to the x is really diverging from p naught of x. So this is a terrible approximation, except at x equals 0. Once you get a little bit away from x equals 0, bad approximation. So I'm not satisfied with a 0th degree approximation. Let's get the 1st degree approximation. P1 of x, which is going to be a naught plus a1x. I have a naught plus a1x because I need that polynomial to be a 1st degree equation, which means it's got to have a constant term and an x term. Yes?
Where did you get the 1 equals a naught?
I had to set this guy equal to this guy. I just want to remind you, my strategy is once I've chosen my center of my neighborhood of the approximation, I've got to make sure that the functional values are equal to each other. That is, the value of f equals the value of the polynomial. So here's my 1st degree approximation. And since I've got a 1st degree approximation, that means I need f of 0, and I'm going to call it f of 0 because I'm centered at 0. I need f of 0 to equal p1 of 0, and I need f prime of 0 to equal p1 prime of 0. That is, I need my function's functional value and 1st derivative to be identical to that of my approximating polynomial. So let's find what those guys are. F of x equals e to the x. F prime of x equals e to the x. P1 of x equals a naught plus a1x. I've already written that down. So P1 prime of x equals a1. Now let's plug in 0 to both of them and set them equal to each other. Are you okay that f of 0 is equal to e to the 0, which is 1, which has to equal p1 of 0, which is a naught? And so again, I get a naught equal 1, just like I got last time. Let's do the same thing with the 1st derivative. F prime of 0 is going to be e to the 0, which is 1. And that's got to equal p1 prime of 0. And I hope you see that p1 prime of 0 is a1. And so I get A1 equal to 1. So by setting the functional values equal to each other and by setting the first derivative at 0 equal to each other, I found what my approximating polynomial is. I get P1 of x equaling 1 plus x. Let me graph that now. This is P1 of x, which is 1 plus x. Do you see that this first order approximation or first degree approximation is better than the 0th degree approximation? This tangent line, because that's what that is, that's the tangent line at x equals 0, it hugs the graph really all the way to there. You know, my neighborhood of it being a good approximation seems to be about from there to there. So that's good. That's better than what I had with my 0th order approximation. But maybe that's not good enough for me. Maybe I want more. Maybe I'm the sort of person who just is never satisfied. So what do you suppose I'm going to do now?
Second.
Yeah, let's get the second degree approximation. Here, I'll do it over here. Here we go. Second degree approximation. So now I'm going to use P2 of x, and that's going to be A0 plus A1x plus A2x squared, because it's going to be a second order approximation. And as before, I'm going to get f of 0, f prime of 0, and f double prime of 0. And set them equal to p of 0. Here's p0, here's p2. So all I need to do is get p2 prime of x, and that's going to be a1 plus 2a2x. You guys okay that that's what the first derivative of p2 is? a1 plus 2a2x. And I'm going to get the second derivative of my second order approximation, and that's 2a2. And now I'm just going to set the functional values equal to each other, the first derivatives equal to each other, and the second derivatives equal to each other at x equals 0, which is where the center of my approximation is. So f of 0, which is equal to 1, is going to equal a0, right? Because when I stick 0 in here, I get a0. Do you notice that what I found previously isn't changing? Like here, f prime of 0 is still 1, and when I stick 0 in here, I get a1. So I still get a1 equaling 1, just as before. But now the second derivative, f double prime of 0, is going to equal 1. By the way, do you see why I chose e to the x as my first function?
Yeah.
Because getting all these derivatives is so easy, and the functional value and all the derivatives are all 1, so it makes it just easy. Okay? And when I stick 0 in here, I get 2a2, which means I get 1/2 equaling a2. So now I have my second order approximation, or second degree approximation, and that's going to be 1 plus x plus 1/2 x squared. Oops. My microwave is plugged in instead of my overhead projector. a second here. All right. Okay, so here's e to the x. And here comes my first order approximation, 1 plus x. And I'll make e to the x, I'll make that thick, I think. In my window, I'll go from like -2, -2 to 3. Okay, and my x-min, I'll go -2. Let me see what I did. I practiced this yesterday. Yeah, -2 to 2 or -1 to 9. Yeah, just a second. Okay, so here's y equals e to the x, and here's my first order approximation. So I want you to see that my first order approximation, my drawing on the board wasn't that accurate. It actually seems to be a good approximation from about -1, maybe -3/4 to +3/4, you know? The first order approximation is good from -3/4 to +3/4. But let's see how good my second order approximation is. We'll do plus 0.5 x squared, because that's my second order approximation, 1 plus x plus 0.5 x squared. So here's my y equals e to the x, and here's my second order approximation. Do you see how my second order approximation is good, like from -1 to +1, or a little bit past +1? So what happened is, by getting a higher order polynomial approximation, I just increased the width of the neighborhood over which my approximation is good. Now obviously my approximation is no good beyond 1, no good beyond -1, but from -1 to 1, or a little bit more than 1, my approximation's good. Let's go ahead and get our third order approximation and see how that works out for us. Okay? So here's what I'm going to do. I'm going to let p sub 3 of x be 1, it's going to be a0 plus a1x plus a2x squared plus a3x to the third. And then I'm going to have to get the third derivative. So this is a1 plus 2a2x plus 3a3x squared. Here's the second derivative, which is 2a2 plus 6a3x. And then here comes the third derivative, which is 6a3. I'll tell you right now, when I'm sticking in 0, I still end up with a0, a1, and 2a2. So my a1, a0, and a1 are still going to be +1. My a2 is still going to be a half. I wonder if anyone can tell me, what's my a3 going to end up being? What's that? Yeah, 1/6. Good for you, right? I'm going to go f the third derivative at 0, which is 1, and that's going to equal the third derivative of my polynomial function, which is 6a3. So yeah, 1/6 equals a3. So let's go ahead and do the third derivative and see the neighborhood over which that third derivative is a good approximation. So I got plus 0.5x squared plus 1 divided by 6 times x raised to the third power. So here's my third order approximation, and let's go. Here's e to the x. Here's my third order approximation. Wow. Here, let me increase this just a second. -3 to 3. So I'm going to go from, -1 is still good, but I'm going to have to go to like maybe 20. So here's my exponential function, and here comes my third degree approximation. Oh, maybe I should go a little bit lower so I can see the bottom of it too. Here, just a second. How about -5? E to the x, third degree approximation. So I want you to see the third degree approximation is hugging my weird function, really from like -2 all the way to almost +2. And so I want to say again that increasing the degree of the approximating polynomial, all it does is increase the width of the neighborhood where your approximating polynomial is a good approximation. Of course, beyond -2 and +2, it's terrible, right? I mean, hey, let's go from -5 to 5 and go to like 100. You know? So here's my exponential, and here's my third degree, and it's pretty much, it's not even close. Beyond 2, my third degree is not even close to my exponential. And beyond -2, if I went down further, beyond -2, again, it's not even close. -50, let's say, you know. But boy, from -2 to +2, it kicks butt, you know.
Mr. Shane,
Yes.
so if you did a fourth degree, the A4 would be 124th, right?
Yep. Yeah. If I did a fourth degree, then a to the fourth would be 1/24th, and the neighborhood over which my approximation is a good approximation would be increased further. Yeah. So hey, that's what we're doing. Now, lucky for you guys, are you going to have to go through this process every time you do this problem?
No.
Heck no. No, I'm gonna teach you a formula where you get to just mindlessly plug in the formula. And the formula is Taylor's formula, Taylor's theorem. And so that's why we gotta learn Maclaurin polynomials and Taylor polynomials. You're not gonna go through this process, but I needed to show you this to let you know this is the theory behind what we're doing. I always want you to be aware of that all we're doing is making sure that the functional value and all the derivatives at that center point line up, are the same. Okay, great. Hey, let's go on. Let's keep going. Let me see what I'm going to do next.
I know, Mr. Shane, was it Zachary Taylor who made the Taylor polynomial?
No. No, but it was Zachary Taylor who was elected in 1848 and died in office in 1850. He led the army in the Mexican-American War. You know what his nickname was?
What?
Does anyone know Zachary Taylor's nickname? Where William Henry Harrison was Teepee Canoe, and so what was Zachary Taylor?
Oh.
He was old.
Old Zach.
Nah. He was called Old Rough and Ready. That's what he was, old, rough and ready. Great man. I think he was the one man who could have staved off the Civil War, but he died in office.
He was just an officer in the Mexican American War, in the Mexican War.
He was a general. He was the leader of the army.
I thought he was just like an officer.
No, he was
I mean,
a general.
it's officer, but like I thought he was a lower officer.
No. I mean, there were officers above him, like General Winfield Scott, but he was the leader of the one particular army that was in Mexico, or maybe in Texas. Oh, you know what? I'm not thinking Mexico. I'm thinking Texas. The war, I mean, that is the Mexican-American War, but he was the leader of the army in Texas. He wasn't the leader of the army that went like to Veracruz or anything like that. Yeah. Okay, and that's how I got famous, and that's how I got to be president. Yeah, he was the slave holder who hated slavery. And so he was it. He was the guy who was going to stave off the Civil War. He hated slavery, even though he's a slaveholder. It's weird. Okay, great. I got to do another one. Just 1 second. Okay. I'm going to do this really, really quick now. So I'd say don't write this down. Okay? I'm going to say, let's approximate f of x equals e to the x, but now centered at x equal 1. You see, I'm going to get an approximation for e to the x, but it's not going to be centered at 0 anymore. It's going to be centered at x equal 1. Well, how do I do that? Let me show you, okay? And I'll say let's get the third order approximation. Let's get the third order approximation. P3 of x equaling a naught plus a1x plus a2x squared plus a3x to the third. Well, I'm still going to have to get all of the derivatives of f of x, right? F of x equals e to the x, f prime of x equals e to the x, f double prime of x equals e to the x, f triple prime of x, and you don't have to write this down, just watch and enjoy, because you're never going to have to actually do what I'm doing. So it's just enough for you to watch, okay? And so the same thing with the polynomial function. I've got P3 equaling this, and so P3 prime of x is going to be a1 plus 2a2x plus 3a3x squared, and the second derivative is going to be 2a2 plus 3, whoops, plus 6a3x, right? And then the third derivative is going to be 6a3. You guys okay with that? And now I'm going to have to set these guys equal to, oh wait, oh my God, I'm so stupid. Oh, I missed the whole point of why I was doing this. I'm glad you're not writing this down. Wow, I like blew the whole point. Okay. Here's the last thing I need to teach you about the conceptual nature of all of this. Did you notice how incredibly convenient it was that when I stick a 0 into the polynomial equation, all of the terms with x's are 0? Mm-hmm. And the only guy left is a naught? Or here, I stick a 0 into the first derivative, and all the terms with x's are 0, and all I'm left with is a1? Yeah. You know what I mean? Like, did you notice how incredibly convenient that all was? Well, what if I want my approximation centered at 1? Now I lose that, right? Now I'm sticking a 1 in, and I'm left with every single coefficient. I've got an equation with a naught, a1, and a2 if I stick a 1 in for x, and that's bad, because I want to be able to stick a 1 in and only be left with one coefficient. So I have to do something weird with my approximating polynomial. I can't call P3 of x a naught plus a1x plus a2x. I need to have a polynomial such that when I plug in 1, all the terms with x's become 0. So here's what I end up doing. I end up going a naught plus a1 times x minus 1 plus a2 times x minus 1 squared plus a3 times x minus 1 to the third power. I have to make all of my x terms x minus 1, because it makes it way, way more convenient to be able to stick in a 1 for x and have all the terms with x's in them go to 0. You see what I mean? So that's the last conceptual thing. I want you to get used to the fact that if they want an approximation centered somewhere other than 0, then all of your x terms have to be x minus whatever that new center of approximation is. So let's go ahead and get the derivatives. P3 prime of x is still going to be a1 plus 2a2 times x minus 1 plus 3a3 times x minus 1 squared. And my second derivative is going to be 2a2 plus 6a3 times x minus 1. And my third derivative is going to be 6a3. So now let's go ahead and plug in. F of 1 equals E, correct? And that's got to equal P sub 3 of 1, which is A naught. So there we go. A naught isn't equal to 1 anymore. A naught is E. Here, F prime of 1, well, that's E. And when I stick in a 1 into P prime, this guy's 0, that guy's 0, and I'm just left with A1. So I get A1 equaling E. Second derivative is going to be E when I stick in a 1 here, I'm getting p sub 3 of 1, and I get 2a2, which means e over 2 equals a2. And then finally, the third derivative is e again, and that's going to equal 6a3, which means e over 6 equals a3. So I now have my third degree approximating polynomial of e to the x, but it's centered at 1. It's not centered at 0 anymore. I get e to the x is approximately equal to e plus e times x minus 1 plus e over 2 times x minus 1 squared plus e over 6 times x minus 1 to the third power. I need to show that to you on the graphing calculator thingy, and then we'll continue. What? Did you see that?
Short circuit.
No, the bulb burned out. Stupid bulb. Do I have a new bulb? By the way, if you're going to fiddle around with a overhead projector, always unplug it first.
That's great.
So,
Are you serious?
what's that?
I would love it plugged in.
Yeah, don't do that. You might get shocked. Let's see if I got another bulb. I haven't had a bulb burn out in so long. Oh, please let this be the same one. Oh, shoot. Shoot, I've got bulbs galore, but not for this guy. I don't think. What am I going to do? I really wanted to show you that. Yeah, I grabbed it by hand. Is this the same one? No. It's totally different. It's hot. Ow, dang it. Ow.
Do they even make bulbs for those projectors?
I don't know. Do we have any of them anymore? It's a good
You're
question.
the only one I've ever seen, besides Miss Locker needs one.
Good. See, that means it's good. Oh my God, they're not even close. Oh man, don't I have it up? Don't I have it like?
Oh, like this.
It's like, and I think I just gave away. Oh no, I still have it. Oh, I still have another. I have a backup overhead projector. That's freaky. But I still can't believe I don't have a. I thought I got an extra bulb of all the ones I have. Wow. Well, no, I don't have it here. All right, let's see if this thing works. Does this thing even work? That's freaky. You see this overhead projector? I used it. I started using it when I first came to the school 20 years ago. It's a 20-year-old overhead projector. Wow.
Mr. Shea, would you think that the bulb in that one works in that one?
No, because the bulbs I was looking at is for that one. It's a different one.
How much do those kind of bulbs run?
Oh, I don't know now. I don't know if I can't buy them, like you said.
Do you think the school would have any extra?
Yeah, I'm hoping so. I know where to look, but I got to do that
You guys have like
on my own time.
teacher supply room?
Yeah. Teacher supply rooms. Like whenever I need anything in my home, you know, batteries or whatever, I just go to the teacher supply room and steal it.
Wait, are you serious? Oh, the TV remote's gone. Guess what?
Well, here a second. Crazy. Oh my God, I'm totally gonna get shocked. Look at that. Frayed, wired.
What?
Let's see if this works. Oh, it's magic.
Oh.
It worked.
That.
Wow, that is small.
It's annoying.
What the heck?
What did you do?
Okay. Boy, that's teeny.
Something's burning.
It's dust. It's burning dust. Okay. Oh my God, it still works. Oh, my precious. You know, you and I have been through so much together.
Although I just do for
That's right, I ditched you for a brighter overhead. You know, that's what you do, which all you young men, remember to do that. You're gonna marry a woman when you're young, and once she starts getting older, go ahead and ditch her for a better overhead projector. Okay, so here's e to the x, but instead of it's being centered at 0, now I've got that guy. So e plus e times x minus 1 plus e over 2 times x minus 1 squared, right? Wow, I can barely see that. That's why I ditched this one, by the way. Plus e over 6 times x minus 1 to the 3rd power. Okay, so you guys okay with that? So now my window, I'm actually going to go from like -1 to 4, alrighty. And I'll still go from -2 to, I don't know, 30. So here's e to the x, and here's my 3rd degree approximation. Okay,
Wow.
and believe it or not, the big thing I want you to see is where my approximation is good. My approximation is good from here to there, right? It's good from about -1 to positive about 3. You see? My approximation is good for the same width of neighborhood as the other one was, but do you see it's centered at 1 now? You know, my good approximation neighborhood, -1 to positive 3, the center of is at 1. So if the portion of the graph that I wanted to approximate happened to be, you know, centered at 1, then I'd have to use this approximation. Is that okay with you guys? Thank you, Barsha. Thank you for nodding your head. That made me feel very affirmed. All right. Well, okay. That's the name of that tune. So now that you get, because again, can I just tell you, so often we teach based on what our own experiences were. And my experience with Taylor and Maclaurin polynomials was I learned it in high school and it made no sense to me. And then I learned it in college and it made no sense to me. Because, I mean, I could manipulate the variables and get right answers, you know, so I got A's on my exams. But no teacher ever took the time to really explain what the heck we're doing with them. The fact that we're getting a neighborhood of approximation, the fact that the C, you know, this, whether it's 0 or whether it's 1, is the center of my approximation, the fact that I'm just making sure the functional value and all the derivatives at that one point are exactly the same for the function and for the approximating polynomial. Like, no one ever told me that. So it was just gobbledygook to me, yes.
So they teach this in college?
Oh yeah, yeah, this is 2nd quarter calculus.
Oh, it's amazing.
Yeah, well, good for you. Yeah, and then that's what this is. You know, everything we learn for the rest of the semester is 2nd quarter calculus. You know how we're learning BC, you know, calculus. This is the C part of the BC, you know. It's the part that's not in AB. Okay. I've got 3 minutes. Let me see what else I was going to do. Just a second. Okay. All right. Hey, I'm going to show you something now, but I'm going to show it to you tomorrow as well, and we're going to really investigate it tomorrow. But I just want you to see it now so it's kind of in your heads so that your subconscious can deal with it. I do not want you to go through this process on every problem. It's a huge hassle, you know? So I'm going to show you the formula for it. And this formula is called Taylor's theorem. I was learning about remote sensing in Science Olympiad. Is anyone in this class in Science Olympiad doing remote sensing? This is impossible. This is, you know, it would take me probably 100 hours of my life to learn this stuff. And I just don't have that time because I have kids and a wife. You know? So sorry, I'm going to show you a couple of things today after school, but you guys are screwed. This is really hard, really specialized stuff. And unless you devote like tons and tons of time to it, I don't see how you could possibly learn it, you know? So here's my notes, all right? And maybe, hey, you know, could you do me a favor and turn off the other light? Thank you, because I'm just showing this, okay? So here's what I'm doing with these notes. I'm actually, actually showing the derivation. So, where did I put my, oh, there it is. So here's what I need you to see. We're now going to get the general formula for an approximating polynomial centered at any point x equals c. This is called a Taylor polynomial. By the way, as you'll learn in succeeding days, if it's specifically centered at 0, then it gets a special name. We call it a Maclaurin polynomial, because this dude Maclaurin thought of these polynomials centered at 0 before Taylor thought of them centered anywhere. Oh, well, we'll just stop now. Hey, Enoch, turn on the light. Thanks.